Okay, it's my great pleasure to introduce Dr. Wei Gao. He's an assistant professor of medical engineering in the Division of Engineering and Applied Science at Caltech. He received his PhD in chemical engineering at UC San Diego in 2014. Afterward, he worked as a postdoctoral fellow at UC Berkeley. He's a recipient of IEEE EMBS Early Career Award, IEEE Sensor Council Technical Award, MIT Technology Review 35 Innovators Under 35 Award, and many more. So I'm gonna stop here. Today, we will talk about his recent research outcomes regarding skin interfaced wearable sweat biosensors. So please join me welcoming Dr. Gao.
Thank you, Hong, very much for the invitation and for the introduction. It's my great pleasure to be here virtually and to share my research on skin interface wearable biosensors. As many of us know, wearable sensor can play a very important role in personalized healthcare because they can continuously collect data from our body and tell us what's going on and what's going wrong with our health. But if you look at commercially available health monitors, like Apple Watch or Fitbit, they can mainly track the physical activities of vital signs, but fail to provide more useful information about our health at a molecular level. So when we think one major gap, which is also a great opportunity right now in this field, is how can we collect the chemical or molecular information continuously and ideally non-invasively? We are mainly looking at human sweat. As many of us know, sweat is a very important body fluid. We can retrieve sweat conveniently, continuously, and non-invasively. And sweat contains important biomarkers, including various electrolytes, metabolites that are closely related with our health. We can also identify more than 30 amino acids, many proteins, vitamins, hormones, and you can also see other substances such as heavy metals, alcohol, and drugs. Imagine that if we could sample sweat non-invasively, right, we could actually potentially get our health information and basically in a non-invasive manner. But sweat test is not something new. It has been there for like several decades. People had been using like a sweat analysis for disease diagnosis, doping control, drug dosage control, genomic studies, and fitness monitoring. But still, some of you may say, I've not heard of many sweat test applications. One major problem for past sweat tests is how people collect sweat. People basically put a patch on the skin. They collect the sweat sample, one sweat sample over several hours or even several days. Then they send this sample into the laboratory, and which will analyze the sample over like a week period. As you can imagine, it takes a very long time, and you can only get 1 point. And this point is the long-term average data. In fact, the biomarker level in sweat changes rapidly. In this case, you don't really get much real-time information. That's why there are a lot of disputes, the controversial about the correlation between sweat and blood biomarkers. The application of sweat analysis is not that many. So one could imagine that if you could develop a wearable sensor, you can place it on the skin like wearing a smartwatch. You can continuously analyze the sweat biomarkers from the skin, and we could use this type of data for fitness tracking, for disease diagnosis, and very importantly, the large set of data collected by this wearable sensor. If we couple the data collection with machine learning, big data analysis, it will enable numerous fundamental and clinical investigations. Recently, we have published several review articles. If you are interested, please welcome to read. So in 2016, I published my first paper on sweat analysis. Basically, we reported a fully integrated wearable sweat sensing platform that can perform in situ multiplex sweat tests. So this system, as you can see from this picture, can perform real-time analysis of multiple metabolites, such as glucose, lactate, multiple electrolytes, such as sodium and potassium. It could also measure skin temperature for real-time sensor calibration. So the whole system can perform on-site signal conditioning, processing, and wireless transmission. So all the data collected from sensor will be sent to the cell phone through Bluetooth and wirelessly and displayed on a customer-developed cell phone app. Eventually, you can save the data to the cloud or send the data to the computer. And since then, we have developed different prototypes. Before I talk application, I would like to briefly introduce several major electrochemical sensing approaches that are being used in wearable biosensors. So firstly, is enzymatic sensors. So let's say if you want to detect glucose, lactate, urea, there are many types of metabolites. As actually, a common way to detect this metabolite is using enzymatic electrode. For example, if we want to detect glucose, so we immobilize the glucose, the working electrode with the glucose oxidase, this enzyme. Enzyme can catalyze glucose oxidation, and we are measuring the current output between the working electrode and the reference counter electrode, basically working and counter electrode. The measure the current is proportional to the concentration of your glucose in the solution or in the body fluid. So if we measure lactate, we can use the lactic acid. If we monitor uric acid, we could use uricase. So basically, there are specific enzyme corresponding to this specific metabolites. We can utilize enzyme-modified electrode to do metabolic sensing. So for glucose sensing, importantly, we use redox mediator. It's basically generation 2 glucose sensor. This push and blue, for example, is one example redox mediator that can lower the glucose sensor operation voltage from 0.6 to 0.7, lower to around 0 volt. Basically, initially, you need to detect hydrogen peroxide, the byproduct of glucose oxidation. Right now, with push and blue, we only need to detect the push and blue redox reaction, which only roughly around 0 to 0.1 volt. The operation voltage is very low. It will miniaturize the interferences from other chemicals. So if we want to detect ions, let's say sodium, potassium, calcium, pH, a common way is using ion selective sensor. So basically, we can immobilize our working electrode with ion selective films. For example, if we want to detect sodium, we can prepare a sodium ion foil containing sodium selective film. For potassium, we use the valinomycin, another chemical selective to potassium. This red text is ion foil specific to this ion. How they work? Let's say if we want to detect potassium, we use the valinomycin as an ion foil. Valinomycin has a ring structure. The ring size is similar to potassium ions. If you put this electrode in the solution contains potassium will go into this ring and set the voltage of this working electrode. So according to Nernst equation, we are measuring actually the voltage difference between the working and the reference electrode. So the measured voltage is proportional to the logarithm of the ion concentration. Let's say if we are measuring sodium and potassium, the charge of ion equal to 1, the slope is 59.16, basically millivolt per decade of concentration. So remember, for glucose, lactate, they are linear. For these ions, they are a logarithm of the concentration. Slope is 59 millivolt per decade. And if we are measuring calcium or magnesium, for example, Z equal to 2, the slope or sensitivity will become 29.6 millivolt per decade of concentration. So in addition to enzymatic electrode and ion selective electrode, we could also monitor targets through voltammetric sensor. For example, for many electroactive molecules like uric acid, some amino acid, vitamin, and drugs, they are electroactive. That means they can be oxidized on a given electrode at a certain voltage. So we can apply this voltage to measure the oxidation reaction. So the current is also proportional. I would say the current amplitude is proportional to the target concentration. For example, if we want to detect uric acid, we can apply a differential pulse of atomic degree. Uric acid will be oxidized at one given voltage. If you look at the first peak on the left picture, that is uric acid peak. So if we measure the peak height, this peak height, the current peak height is proportional to the uric acid concentration. So we can convert back to the target concentration. These are three main methods used for wearable electrochemical biosensing. So we introduce the background and basic mechanism. So we can package the integrated system into different form. It could be a smart wristband, could be a smart headband. We can wear the device at different body parts. So here I also show our one of the developed mobile app. Basically, it's an Android app. You can pair the electrode, pair the sensor with the cell phone. You can real-time read your target concentration from your phone, and you can also check the progression profile of each analyte. So eventually, you can save the data in the phone or send the data to the computer through email. So with this integrated system, you could continuously collect data from your daily activity while you're doing exercise. So it can be used for many applications. Some examples including kidney function monitoring. Let's say calcium level is a very important biomarker for kidney function. People actually, previous reports show that the sweat calcium level for the people with the kidney problem will be twice as high as healthy people. But monitor calcium directly in sweat using ion selective electrode, basically you're measuring calcium ion, which is not fully accurate because you want to get a full calcium level. Some calcium is ion, some calcium not even ion formed. That's why, because calcium ion level is depending on the pH. When you have lower pH, you have higher calcium concentration. That's why to get an accurate calcium profile, ideal to monitor both calcium and pH together. So that's why we propose this multiplex system. You can monitor calcium and pH simultaneously through this sensor array. And we actually validated the sensor with commercial pH meter and ICP-MS, showing our sensor can really get accurate information. We can get a simultaneous measurement, and this could be very useful for kidney function monitoring. Another application is heavy metal monitoring. Like we are exposed to heavy metal every day. They are closely related with our health also. Some of you may still remember in the past, several years ago, the water crisis in Michigan Flint has already caused many children's health problems because of the lead contamination in water. So basically, even through our food intake and water intake, or even if you are social level, let's say you may be exposed to high mercury. So we are exposed to heavy metal every day. And our sweat is a way to detoxify ourselves, basically. Sweat contains heavy metal, but the level is pretty low. How can we detect heavy metals in sweat? One of the methods is using anodic stripping vitamin. Because their concentration is very low, so we need to pre-concentrate these ions. So basically, by applying a low voltage, the heavy metal ions will be deposited onto this microelectrode from a heavy metal film. This heavy metal film can be oxidized at a given voltage again. If you apply voltage from low to high with differential pulses, each heavy metal will be oxidized into ion back again and at a given voltage. By reading the current height at a given voltage, you can get this specific heavy metal concentration. So based on this, we can get 5 heavy metal simultaneous monitoring. The whole sensor array, as you can see, is very small. So till now, many people may have a question. Since you are doing sweat sensor, what if I don't have sweat? Because most of the time, accessing sweat need a vigorous exercise, right? Or if you want to do a clinical study, what if the patient cannot even do exercise? So these are very good questions we have to address to make sure our device can be used by most people, right? So we actually found a process how to induce sweat beyond physical exercise. And through a process called interferences. In a clinical setting, the doctors use this process to induce sweat. Basically, by using this equipment, you can apply a current through the skin, and you have the other hydrogel on a 2 electrode. When you apply positive current, the positively charged drug molecule will go with the current to enter below the skin and actually stimulate the sweat gland, trigger local sweating. And the clinician usually collects the sweat using this microdot collector. Then they send this sweat for a laboratory to analyze sweat chloride. This is used for cystic fibrosis diagnosis, which is a lung genetic disease. Sweat chloride is the gold standard for CF diagnosis. So inspired by this process, we developed an integrated system that includes the interferences module and the multiplex sensing. So basically, all you need to do is control from cell phone. When you want to do sweat analysis, click a button from cell phone, and this interface module will be triggered. And the mode 1, when a small current will be applied through the skin between the interface's electrode, and you only need to apply several minutes. Then sweating process can last pretty long, could be hours. So basically, you can repeat this process over time as well. You can imagine in this case, you don't even need to do exercise. You can just do computer work, and you can still get continuously the sweat and get data from your sweat sensor. So in collaboration with the Stanford School of Medicine, we characterize how different type of drug will influence the sweating process. For example, the most commonly used drug, pilocarpine, is FDA approved. Most of the time used on the infants, so it's pretty safe. So every drug, you have different profile in case of the sweating. As you can see, if you control the drug dose or drug types, you can actually tailor the sweating profiles. If you look at some parameters like a response latency, it means after you apply current, how long sweat will come out. If you use the pilocarpine, the red one, 240 seconds. That means after 4 minutes you apply the current, sweat starts to come out. But if you use acetylcholine, this process only takes 52 seconds. That means sweat nearly immediately come out after you apply current. You can get a very quick sweat process. By control these drug types and drug dose, you can control how fast you sweat, how much you sweat, and how long you sweat, basically. So you can also, as I said, repeat this process on demand, depending on application. So in the following slides, I will be sharing with you some applications of using sweat sensor for clinical studies, basically. The first one is disease diagnosis. I briefly mentioned sweat test, basically sweat chloride, is a gold standard for cystic fibrosis diagnosis. So clinically, people need to wait 1 week to get a sweat chloride. Working with Stanford Cystic Fibrosis Center, we applied our device on the healthy people and on the patients, as you can see here. For the healthy people, if we are measuring sodium and chloride over time, basically we induce sweat and measuring sweat, within 20-25 minutes, you can get a sodium chloride level. If you look at statistical value, healthy subject sodium chloride levels are much lower compared to patients. Right now, the gold standard for adults for diagnosis is based on sweat chloride higher than 60 millimolar. From the data, you can see that our device can be successfully used for CF diagnosis. In a very short period, you don't have to wait 1 week. You just need 20 minutes, 25 minutes, you can get all the data from beginning to confirm the diagnosis. So we could also use the wearable sensor for metabolic and nutritional monitoring. And we believe this is a major direction we are going. And metabolic syndrome right now is affecting 1/3 US adult population. The risk factors for metabolic syndrome includes, high blood pressure, high blood sugar, unhealthy cholesterol level, obesity, and high uric acid level. These kind of risk factors could trigger metabolic syndrome. And metabolic syndrome are by itself risk factors for more severe problems such as type 2 diabetes, cardiovascular disease, and kidney diseases. And one of the most important reasons for developing metabolic syndrome is diet and lifestyle. So basically, wearable sensor can play a very important role for monitoring, preventing, and performing the intervention to minimize the chance for people developing metabolic syndrome. In this case, what we are looking at is circulating metabolites and nutrients, because these are key parameters or biomarkers for metabolic syndrome. So one of the most important biomarkers, of course, is glucose. Everybody talk about the glucose monitoring. Right now, you have finger prick glucose monitor. You also have continuous glucose monitor based on implantable device, basically the needle using like from Dexcom, Medtronic, for example. But both methods are kind of invasive. The non-invasive approach will be very attractive. Then people ask, can you really monitor glucose non-invasively from the skin? We actually did some pilot study. As you can see, if you give the subject a glucose diet, basically, you can compare fasting glucose and after glucose intake between sweat and the blood glucose level. You can see a similar pattern over time. Basically, this type of sensor enables a correlation study between sweat and blood biomarkers. we still working on this topic. By itself, glucose monitoring is a bit controversial in sweat because the correlation is good, but not good enough right now. We need probably more in calibration mechanism to get a better correlation. But an interesting story is I was approached by a beekeeper in Texas, actually. In his email, he's saying, with diabetes patients, I'm looking forward to trying out technologies. I'm living in Texas. I'm sweating all the time. Basically, I clearly know that the bees like my sweat more than the others because diabetes patients, their sweat is sweeter. So very recently, to monitor a broad spectrum of low-level metabolites and nutrients at larger scale, and we actually introduced a new platform of fabrication method. So we proposed this mass-producible laser-engraved wearable sensing platform for simultaneous sweat sampling, chemical sensing, and vital sign monitoring. How this work? Because many metabolite nutrients, they are very low concentration and very low concentration. To monitor this, you need highly sensitive sensors. Then typically people do different nanomaterial modification, right? But when you do nanomaterial modification, you will cause more variation because it's a manual operation process. For wearable sensor, ideally the sensor should be highly reproducible. You don't have to calibrate every sensor for the subject use, right? So basically, by using laser engraving, we can fabricate the graphene-based electrode at larger scale, high performance, and low cost. As you can see, this is one picture showing all these sensors. And based on this graphene structure, we can fabricate physical sensors to monitor vital signs, including respiration, heart rate. We could also make highly sensitive chemical sensor based on graphene for detect electroactive molecules. We could also use laser to fabricate microfluidics, which could efficiently sample sweat. As you can see, this is a multi-inlet design. Why we need the microfluidics? Because people may have concern, what if sweat evaporates? What will happen if your old sweat mixed with new sweat, right? With microfluidics, you will minimize this kind of problems because there is limited evaporation, everything in the microfluidics, and you will also have always newly secreted sweat will flow through the sensor and push away old sweat. You get near real-time information. So again, this method is very low cost. All you need is the CO2 laser cutter and the polyimide substrate. So basically, laser will directly carbonize the polyimide to form this graphene structure. So as I said, this microfluidics is very important for efficient sweat sampling. So we designed this multi-inlet microfluidics. Secreted sweat will enter the micro reservoir. The sensor is in this micro reservoir to perform real-time analysis. We did simulation and the experimental measurement. We found that basically 2 to 3 minutes, that's a potential delay for the sensor measurement. But 2 to 3 minutes we think is good enough for wearable continuous monitoring because we don't really care 1 to 2 minutes time resolution in most of the cases. So we, as I said, we usually do integrated system rather than only like a sensor electrode. So we did a system integration. This is my student. He wears a sensor, integrated sensor at the wrist and at the forehead, and we can real-time read the analyte concentration from the phone. And we also did a validation of our sensing accuracy with HPLC. When you measure uric acid, for example, we use HPLC to measure and use our sensor to measure, we get a very high linear correlation. So during the continuous physical activity, you can measure the biomarker level continuously, as you can see here. You can see 2 peaks, in fact, from this figure. The first peak belongs to uric acid. The second peak belongs to another amino acid, tyrosine. Both are very important for our health monitoring. For example, tyrosine, people reported that for the trained people, their tyrosine level is much lower than healthy people. So based on this, to verify this conclusion previously demonstrated, we actually recruited Caltech athletes on campus, and we also recruited untrained subjects. As you can see, for the untrained subjects, the red dot, their tyrosine level most of the time is much higher than trained athlete team. This is a successful validation of our sensor can actually be used for this type of investigation. To show this sensor, because this part of the topic is the metabolic disorder monitoring. So we picked a major health condition, gout. Gout is the most common inflammatory arthritis affecting tens of million population around the world. My brother has gout as well. It's quite painful, especially if you are a gout patient and you are a beer or seafood lover, because when you take more pure and rich food such as seafood, red meat, or beer, the patient will get a gout attack. It's quite painful. And gout is characterized by hypoglycemia, basically high uric acid level. Too high, they are basically crystallized near the joint. It causes a lot of pain. So, for gout patients, they also, many times take medication to lower the uric acid level. But again, it comes to the question, how much you want to lower? If you take too much medication, it's very dangerous. If you take too little medication, you still could get a gout attack. It's very important for healthy people to monitor uric acid to minimize the chance for developing gout. It's also very important for gout patients to monitor this to determine whether they could take or how much they could take pure rich food, or how much medication they need to take to control the uric acid at proper range. So we use our laser-engraved graphene sensor platform to monitor sweat and serum uric acid. As you can see, before and after food intake, you can get a very clear difference and a very similar pattern between sweat and serum uric acid level. And we recruited a patient with gout and a subject with hypoglycemia, and healthy people as well. You can see a very similar pattern. You can see serum, sweat, uric acid level. And for the patient, they have much higher uric acid compared to healthy people in both sweat and serum. If you track one subject, one person over time, for 7 hours, you see when the person take a pure rich food, the uric acid level both in sweat and the blood increases and then decreases over time. You see a very similar pattern. If you plot all data together, you get a high correlation factor of 8.864 between sweat and the blood uric acid level. It's very high correlation. This is just one example. We are monitoring actually different kinds of metabolic risk factors, and our goal is really enable early diagnosis and early screening of this metabolic disorder, and potentially with the help of the wearable device, enable nutritional intervention. Basically, you just need to change your diet or change lifestyle. For example, if you have insulin resistance, you're on the way to develop prediabetes and diabetes. By changing lifestyle and food intake, nutritional intake, you could reverse the trend of developing diabetes. So the third application I want to share with you is using wearable sensor for therapeutic drug monitoring. Drug dose personalization using wearable sensor is a main direction for our research as well, because in the future, precision medicine, ideally the physician need to tailor the medication according to each patient, because drug metabolism vary person to person. For adults, if you compare metabolism of drug of the adults versus a child, obese subject and a very thin subject, as you can imagine, the metabolic rate could vary by several times. But right now, what doctors can say is every day you take one pill, take two pills, there is really very few personalization process getting involved. But many drugs, in fact, have very narrow therapeutic window. What is therapeutic window? Basically, when you take medication, if you take too high concentration, you will experience strong side effect. If you don't take enough medication, you don't get effective treatment. Both too high or too low could be life-threatening in this case. Ideally, you want the drug maintained within a given range. But many medications, in fact, the therapeutic window is very narrow. You need to control it. But how people do it? You have to come to the clinic, take blood draw once a week to get this point of the drug level. But the drug level will change all the time, right? It's not very convenient to do this type of study. And it's nearly impossible for a rare disease to do this therapeutic drug monitoring because you don't get enough sample. So wearable sensor could be an attractive approach because many medications secreted through sweat, and they have very good correlation between sweat and blood ones. You basically can use the wearable sweat sensor to continuously monitor the drug level in your body. So before we found a good clinical collaborator several years ago, what we can do is find a model drug, caffeine. Caffeine is a drug, and caffeine is something we can easily design a human study. Basically, ask the students or subject take coffee. So you could take 1 shot of coffee, 2 shot of coffee, or even 3 shot of coffee to see how much, but basically control your caffeine intake. You can monitor caffeine secretions through sweat. And we designed this caffeine sensor based on voltammetry sensor I mentioned before, because caffeine is the electroactive molecules. We can oxidize caffeine near 1.4 volt if you use a carbon electrode. So we can get very high sensitivity in a few micromolar caffeine you can monitor. And over time, you could wear this sensor to see your caffeine level in your body, as you can see here. Basically, it tells you after you take coffee, in the first hour, the caffeine level increases over time and reaches the first peak actually at around 1 hour. That means probably you feel the best at that time. You have higher caffeine in your body. So this is just one example. Right now, we have a great collaborator at City of Hope. We are monitoring different type of cancer drugs. It's quite a promising result as well. So the fourth application is also very important one, using wearable sensor for stress and mental health monitoring. So some of you might not know, 95% of diseases are related with stress. Anxiety, depression, PTSD, cardiovascular diseases, cancers, they are all related with stress. Basically, right now, the depression is a major depressive disorder already affecting more than 200 million around the world. For PTSD, they are affecting 6% to 9% of U.S. population. For both, people experience more mental issue during the COVID-19 pandemic because, there are a lot of issues. People stay at home, don't have no access to many friends and a relationship. There are more mental issue coming out this year. But how stress and mental health or mental disorders monitored, they are mostly based on questionnaires. For example, for stress, you actually have PSS and POMS, this different type of questionnaire you can get your stress level. For depression, there is a PHQ-9 also. Basically, it's another questionnaire to diagnose if you have depression or not. As you can imagine, these questionnaires are very subjective. It's similar. A similar issue is the pain test. When people ask you how painful you feel from 0 to 10, every people can have a different answer, even they experience a very similar pain level, right? And because it's a subjective questionnaire. And people also use, vital signs to monitor stress, but that usually cannot be a condition specific. Of course, there are a lot of work need to be done in that period. But we are looking at, can we actually monitor biomarkers, stress biomarkers from our body? Like a stress hormone. Of course, they are most important biomarker for stress monitoring. That's the reason why they call stress hormone, right? Like from cortisol, when you experience the stress, the cortisol gets secreted and increase in your body, and also actually could reflect reflected from your saliva and sweat secretion. Cortisol level is a reflection of stress level, and also cortisol change over the day. Morning cortisol is high, afternoon cortisol is low. The circadian rhythm of the cortisol is related to mental and metabolic disorders. For example, depression patients and PTSD patients, their cortisol circadian rhythm is different from healthy people. So we developed, using our laser-engraved reference system, developed this point-of-care telemedicine-based cortisol sensor, which can perform sensitive and selective cortisol monitoring in body fluid in less than 1 minute, basically. So using this sensor, we could non-invasively access cortisol through human sweat. Why we need a sweat? Why not using blood draw? Because people use blood to collect blood to monitor stress, but as you can imagine, the blood draw itself, this process is stress-inducing. People experience more stress when they take blood. That make your blood hormone level not very accurate, not actually reflect your stress status before you do blood collection. So sweat will be a very attractive non-invasive source for stress monitoring. And we actually characterize the stress hormone dynamics over time. We can see in sweat, it's very similar to saliva and blood, morning always higher than afternoon. And if you track one subject over 6 days, you can see always morning, afternoon, the circadian rhythm clearly demonstrated in this figure from this subject. And we can have identify actually a very high correlation between sweat and serum cortisol level is, again, correlation factor is 0.87. pretty high already. We are the first one to characterize these dynamics over time of stress hormone in human sweat. Not only we found a high correlation, we actually thought about if we could validate if our sensor can capture the rapid response, rapid changes of the cortisol level during stress response events. That's why we designed more human studies. We actually applied different stressors to the subject, give people stress, in fact. For example, aerobic exercise is a stressor, and the cold pressure test is another stressor. When we increase the stress, we actually can quite quickly check the stress hormone level in sweat using our sensor. As you can see, during exercise, during cold pressure test, we both rapidly detected the cortisol increase using our sensor, indicating that this sensor can be used for rapid stress tests, and very importantly, it opens the door for mental health diagnosis eventually for future applications. And I want to mention that for the cold pressure test, it's the standard pen test, in fact. So you put your hand into ice water, you will feel pain and stress, in fact. I was the first subject in my lab to do this study. Well, not an official subject. When I first time try, all my students actually are looking at me, making me even feel more stressful because in the first minute it's quite painful. I really want to bring my hand back. But everyone looking at me, making me like, okay, more stressful, but I have to stay longer. Eventually, I realized why they're looking at me, because everyone, they put $1, they just bet how long my hand can stay inside. So, our sensor in this case, we are right now working with NASA to use this technology for mental health monitoring of the astronauts in space. So, not only we are working on developing novel wearable biosensors for health monitoring through chemistry material innovation, we are also trying to address the challenge, one major challenge for future wearables. How can we power future wearables? Well, people could think about the battery. Battery, you need to recharge. Not all the place you have place to recharge a battery, especially, let's say, for the soldier or fighter, they perform tasks in the field. There's no much accessibility for electricity. You could say near field communication, but you need to put your phone very close to get electricity using near field communication. So then things come into our mind. Since we are doing sweat tests, can we use our sweat to power the whole wearable? The answer is yes. Very, very recently, we developed a biofuel-powered electronic skin. Actually, this is the first time we demonstrate a battery-free biofuel-powered electronic skin can perform multiplex biosensing, signal processing, and Bluetooth wireless communication. Bluetooth wireless communication consuming very high power. So how can we achieve that? Right? We have to address issue because biofuel suffer challenges from low power density and low stability. So actually, through material innovation, you can see here we use from 0D to 3D nanomaterials on both anode and cathode. On anode, we actually immobilize carbon nanotube on top of graphene, graphene on the top of a 3D nickel structure. On the cathode side, we use platinum cobalt nanoparticle on top of carbon nanotube network. In fact, we increase the anode surface by 3,000 times, and we can get very high power density out of these biofuel cells. Actually, what we achieve in raw sweat from subject, the record is 3.6 milliwatt per centimeter square. As you can imagine, per centimeter square is a very small area. You can get several milliwatt. The power density is by far record breaking, basically the highest recording in the literature for wearable sensor in raw biofluid. So not only we can get a very high power, we can also get a very high stability. So one of the issues for previous biofuel cell is poor stability is the cathode. The cathode get poisoned and get decreased performance over time. If people use platinum, it get poisoned. If people use the silver oxide, it get consumed. Basically, by using platinum cobalt, this alloy on the cathode, we actually show that this resistance can last very long, as you can see. Over time, if you common platinum, the first hour is basically the performance decreases very rapidly. But with our current design, the nearly stable and remain unchanged the performance over time. You can use this biofuel cell for a very long time in raw biofluids even. Here we show firstly like a 15 hour, then we wait 24 hours, then take another 15 hours. Basically, the performance is nearly the same after so long-term continuous operation. So we get high enough power. How can we power, wearables, right? Wearables could consume a lot of power. What if the biofuel cell some period do not generate enough power, right? That's why we did interesting energy harvesting, storage, and management in this case. Basically, the biofuel cell will go to a DC-DC converter and charge a capacitor. When they charge the capacitor to a certain voltage, the capacitor will power the wearables in a short period, collect data, send a package, then it go back to the charging period. If the sweat contains enough lactate, it could continue to operate. If the sweat doesn't really contain enough lactate, it could, charging, powering every second using the data, not needing every second, for example. So basically, most of the time, the system is in a deep sleep like operation. It only takes 2 microampere, very low power. And in active mode, it only active for 10 milliseconds, do the measurement and send a package. So this is how the system works. So we did the integration on the soft platform, and we did all the IC on the polyimide as well. Eventually, we use PDMS to encapsulate the whole system, the waterproof. And the sensor is super stable, as you can see. This is continuous charging for 50 hours. And this is continuous charging in sweat for a day. And we actually show that you don't even need much lactate to power system. All you need, because lactate concentration will affect how fast you do a measurement. If you have 20 millimolar, you can do very quick measurement, charging, discharging. But if you have very low lactate, 5 millimolar, you can still do operation 20 seconds, 30 seconds to do a measurement, which is still good enough for most wearable sensing applications. So with this system, you can continuously collect data. We designed this urea, ammonia sensor, glucose, pH sensor. You can use this battery-free system, continuously collect data. And very recently, in collaboration with Professor Azita Imami, an electrical engineering professor at Caltech, we developed these systems, integrated circuit. Basically, as you can see, this integrated circuit only has a dimension of 1.06 and by 1.32 millimeter. Very small. Including the biofuel cell, the fully packaged system is only 5.5 versus basically 6.2 millimeters. It's very small. So you can, efficiently harvest energy from lactic acid and perform signal processing and wireless communication. So the whole system is very low power and very small dimension. As you can imagine, with this power consumption and size, we can integrate many more sensors on this platform. So in addition to using sweat as a power source, we could also harvest energy from human motion by using triple electrical nano generator. For example, we are using a flexible printed circuit board based FTNG. We can harvest energy from body motion. And with similar energy harvesting process, we could also power this wireless system continuously, and including Bluetooth communication. It's a very similar approach we demonstrated using biofuel cell. And as you can imagine, we could even combine both together to power system. While you don't do exercise or don't even have sweat, you could use motion to power the system. And when you have sweat, you use biofuel cell. This could be a hybrid system. So both doesn't really need a battery for this full wearable system. So the last example I want to share with you is not on our progress on wearable sweat sensor. It's about using a similar technology we used for our wearable sensor. The one we talked about, the laser-engraved graphene system we use for uric acid and cortisol detection. We actually recently, to address the need of urgent, quick, fast tests for COVID-19 diagnosis, we developed this graphene-based multiplex COVID-19 monitoring system. We call it SARS-CoV-2 Rapidplex. It's a mass-producible platform, very low cost. This whole graphene electrode multiplex sensor array costs 5 cents. So basically, this platform can simultaneously monitor different categories of COVID-19 biomarkers, including SARS-CoV-2 antigen, which tells you whether you are infected right now or not. We could monitor virus antibody, which tell you the immunity, whether you have previously get infected with COVID-19 or not. We could also detect inflammatory biomarker, which actually tells information about the severity of the infection. So this single multiplex sensor patch can perform the simultaneous monitoring of 3 categories of biomarker, which could tell us the infectious stages, severity, and immunity. Basically, this device tells all the information within 10 minutes. Basically, all you need to do is just a drop of blood or drop of saliva. So very rapid test and low cost. It's ideal for in-home remote COVID-19 tests. So to summarize, basically, mostly today I demonstrated our wearable sweat sensing platform for personalized healthcare. We developed this platform to continuously collect data, different biomarkers from sweat, and we could use this information for fitness tracking, disease diagnosis, and very importantly, it opens the door for many numerous basic fundamental and clinical investigations if we couple the data collection with big data analysis, because right now we have a lot of data from vital signs, but we do not have data from chemical side or molecular side. That's a missing part of the information. So in the end, I would like to thank my group at Caltech. This is my group like a year ago already. Thank our collaborators, past collaborators, and current clinical collaborators at different medical centers, including UCLA, Cedars-Sinai, City of Hope, and USC medical centers. And also, I would like to thank our funding support. Thank you, everyone, to be here to listen to my seminar. I would like to take any question you might have. Thank you.
Thank you very much, Professor Gao. We really appreciate your being here. I'll remind attendees that they can post questions in the Q&A box, and we have one question already. So the question from Mohammed Hassan: How does the mixture of old and new sweat affect the sensor output? And then secondarily, does it require any calibration for acquiring accurate results?
Mm-hmm. That's a very good question. So regarding the new sweat and old sweat and new sweat, I demonstrated this microfluidic design. Basically, sweat analysis suffer from, sweat could evaporate. Also, like this question raised, old sweat can mix with new sweat. So that's why we need a microfluidics. So when the new sweat come out, it will push away the old sweat. That's why, it will flow through the sensor. For example, like the sensor is here. When the sweat coming out, it will flow through the reservoir and go to the outlet. So we did a simulation. This is refreshing time. We did also actual study. If you have one concentration in start with, you change your concentration, you can see how fast the new solution will push away old solution. You get a new measurement. Basically, the time of delay or time for response is around 2 to 3 minutes. In this case, you get a near real time like a measurement. Regarding calibration, I think this is how to get a new sweat like a reading. Regarding calibration, certainly sweat biomarker or sweat sensor reading could be influenced by temperature, for example, and it could also potentially influenced by sweat rate. So we actually have a temperature sensor. If you remember in my first example, from our first batch, we already included temperature sensor. Basically, in all our wearable sensors, we have a temperature sensor on board. Basically, you could real-time read the temperature to do the real-time sensing calibration. And depending on the biomarker, and some will probably need more calibration to get a better correlation. And as I demonstrated, we already get a pretty good correlation on many biomarkers. By introducing more calibration mechanisms, such as sweat rate calibration, potentially we could get even better correlation. Because some biomarker level will be influenced a bit by sweat rate, how fast you sweat. Yeah. Thanks.
So the next two questions are actually related, and I'll read them both. So the first part from the first person, Nathan Rodevere. Increased sweat reduces adhesion of the device to the skin. Do your devices rely on straps to stay in place, or have you found materials and designs to solve this problem? And then related to that, from Chi, can wearable sensors be used in water? And I think, so those are both kind of related to the adhesion issue.
Yeah, how we do this is a patch. Basically, we have this, let's say, sensor design. Basically, this can be attached on the skin. On the top, you have adhesive layer. So what we are using is like a medical tape. So it's transparent, directly attached to the skin. It's like a bandage. You can imagine when you wear a bandage, it can last several days. So it's waterproof. waterproof. When sweat come out, it just enter the microfluidics, and you can do the sweat measurement. And when you do not need a distance pad, you can just peel off, like peel off a bandage. So basically, how good the adhesion is, depending which type of tap you pick. This is something very tricky and very interesting. And there are very good taps from 3M, for example, you can use. It's medical grade and biocompatible, and you can place on skin. And again, most of the sensors are not intended for using many days. Let's say the electronic part certainly they're reusable, but the sensor electrode, you could replace the electrode or sensor patch every day or every several days. Just peel off and replace with another one. It takes only a few seconds for you to replace.
Okay. Next question is from Pulak Bhushan, who says, for the uric acid sensor, you showed clinical readings every 15 minutes. So do you remove the sensor and collect the sweat to carry out the HPLC testing?
Oh, so for the HPLC test, this is not on-body test. This is just for sensor validation. So we collect sweat from the skin, and we do the same sweat sample, basically analyze and use the sensor, and analyze and use HPLC. We just compare the sensor reading in the same sweat sample is the same or identical with the HPLC reading in this case. It's not on-body.
Okay. From Paolo, the question is, what sensing platform was used for cortisol monitoring?
So for cortisol sensor, by itself right now is not a wearable system. As I said, we call it a telemedicine biosensor. It's based on antibody. So basically, we immobilize the cortisol antibody on the graphene. And this is the antibody, of course, is very selective to cortisol, and it will bind to the cortisol. Right now, it's one-time use, but the detection speed is very fast. We just need 1 minute to get the cortisol reading. So from this method, we can still get near real-time cortisol sensing. Yeah, and our goal is really achieve continuous monitoring for cortisol as well. That's why we are on the way to do that.
And the question that I'll ask as a follow-up to that is, so what is the largest analyte you can detect through skin?
So yeah, that's a good question. So most of, as I said here, as the skin contains many important biomarkers. People find the hormones, peptides, these are small molecules, but people also find proteins. For example, relatively small proteins like cytokine, TNF-alpha, you can find from the skin. And very recently, we can also even find some large protein like CRP, But when you detect the large protein, their concentration is much lower, of course, because large protein is harder to secrete through sweat gland, and they're present at much lower concentration. So it's much harder for developing a wearable sensor to analyzing the protein from the skin. But if you collect sweat from the skin and run like a mass spectrum, let's say, people identified 300 proteins from the skin. In fact.
A follow-up question from Pulak Bhushan. Could you suggest how these wearable sensors can be validated against gold standards if continuous readings are taken on body, since the sensor functionality may change when placed on body for multiple days?
Yes. So when we say like a calibration, the gold standards for most of our application is versus blood, right? Like we take the reading from a wearable sensor, and we also collect blood using finger pricks. Actually, for example, uric acid, we do this way. We compare our sensor with blood. If we get high correlation over time, still we would be able to trust our sensor. And regarding how long the sensor lasts, when you say several days, most of the chemical sensor will not be able to last several days without significant sensor drift. But actually, we are making some good progress. Something that can last super long now. But the realistic case is we don't have to wear a sensor or wear a patch for very long, for like many days, as I mentioned earlier, because we make this platform mass producible and low cost. So you basically only need to replace this low cost sensor patch, let's say every day or every several days. We do not even want to do calibration if the cost is low enough, right? You could easily take a few seconds, change a new one. Right now, like we charge even like our Apple Watch, every day we need to charge. But in case the sensor, right, taking that time, just take a few seconds, we could change the sensor every day or every several days.
Great. I think we've reached the end of the hour, so I'm going to say thank you very much to Professor Gao for joining us from Caltech and to Professor Yao from Georgia Tech for inviting him, and thank you all for attending. And remember to join us in 2 weeks for our next speaker, Khalid Saleta from Emory University. Thanks again, everybody, and have a great day.
Thank you, everyone.